Hey, I hope you're with me. So let us continue this whole discussion on the effect of the Prandtl number, right? So we said we are going to look at the limiting cases. One where the Prandtl number is very large, 1, and the other case is when the Prandtl number is very small, right? Because it it gives us a lot of it helps us in getting a lot of simplifications in the calculations, right? So let us see what do I mean by that. And here, of course, the standard case where the wall temperature is constant is going to be considered. Okay, that's what I'm going to look at. Okay, so now. So let's see. Okay, so now, so when I say that Prandtl number is very small, so what did I say here? The Prandtl number is very small, which means that delta thermal is very large, and which also means that delta x is very small. So let's sort of draw that. What does that even mean? Let us sort of draw that a little bit. Okay, now let us see if this makes sense to you. Okay, so now, okay, that's my, plate, okay, and this is case 1. This is case 1, okay, where the Prandtl number is very small. Okay, it is very small, okay, which means, and what we've seen earlier, so what that means is that delta H is very large. The thermal boundary layer thickness is very large, which means delta thermal is very large and delta is very small, right? The velocity boundary layer. So what does that mean? Okay, what does that mean? Which means essentially, so let us draw that. Okay. Okay. Now, so the boundary layer, the velocity boundary layer is very small, right? That's what is said, which means that, okay, this is my boundary layer. Okay, so this is the free stream velocity, okay, and essentially it is this height, okay, right, till which we have a velocity, a differential velocity, or we can say it is in this region basically we have this. And right after this, the velocity here is again v infinity, right? So it's as you can see, the delta x is very small. Okay, delta x is very small. Now, the thermal boundary layer, however, is very large. Okay, so what does that mean? So what that means is that, say, I have this as the wall temperature, okay, and this is my free stream. Okay, or even further, if I were to sort of exaggerate this a little bit, so let's say it is something like this. Let me exaggerate that a little bit. So what that means, okay, I'm not sure why I'm not getting straight lines here. I'm trying to draw them as best possible. So this is the free stream, and this is essentially the wall temperature, right? This is the wall temperature, and this wall temperature, therefore, and there is a certain heat transfer, and at this height, basically, you get T alpha. This is the first time you get T in the free stream. So therefore, in this case, okay, in this case, this height is the height required, okay, for the temperature to go from the wall temperature to the free stream, and that is the thickness of the thermal boundary layer. So therefore, this is a kind of picture that one can visualize if the Prandtl number is very small. So the Prandtl number is very small, so the velocity will quickly reach the free stream velocity away from the wall. Okay, so this is how it will look like. However, the temperature, the wall temperature, it extends, like we had said further earlier, that it extends. It's quite large into the flow field, and it goes. It takes about this height, delta TH, to reach the free stream temperature. Okay, so similarly, we're going to talk about if the Prandtl number is very high. Okay, so let us look at that. So again, we're going to draw the same thing. Okay, this has to be a flat plane. I'm not able to draw a straight line at all. Okay, so this one is again, this is case B. Okay, here the Prandtl number is very large. Okay. What does that mean? It's very large, and so which basically means that delta is very large and delta TH is very small. Is that right? So in that case, so let us therefore okay, so delta is very large. So what can we say? So therefore here something like that. So therefore okay, and this is basically the free stream velocity. Okay, it reaches there the first time. So here actually this is the height of the fluid which is required for the velocity to go from 0 to V infinity. So therefore, this is the height of the velocity boundary layer. Okay. Now coming to the thermal boundary layer here. Okay. So what basically happens is that it reaches the okay, so this is right, this is the free stream, right, which reaches it right here. Okay, this is also free stream. So therefore, it reaches okay, right about, so this is your thermal boundary layer, and this is your wall temperature. Is that right? Okay, so therefore this is your thermal boundary layer. So this is what we kind of are looking at, in terms of, writing this out. I mean, graphically, trying to get a picture of what we're talking about. So now if you see, so therefore if you have a picture something like this, so if you had a picture like this one, like A here, right? So the first thing you could actually say, oh, so that's the case. So, delta x is very small, delta th is very high. Oh, that means the Prandtl number is very small, okay? So on the other hand, if you have something like this, so then you would say, oh, so the delta is very high, the delta th is very small, so therefore the Prandtl number is very large, okay? So that's what physically this means, okay? Prandtl number being very small and very large. Okay, so now let us see. Since we said that it also renders some simplifications in calculations, let us see how that shapes up. Okay, so this is the case where Prandtl number is very small. Okay, so this is the case where, so we're going to talk about this. Prandtl number Okay. Now, in this case, okay, when Prandtl number, okay, is very small, which means now you see the delta in this case, the thermal boundary layer is much boundary layer thickness is much larger than the velocity boundary layer. Therefore, therefore, what we can do here is that we can disregard the velocity boundary layer when calculating the thermal boundary layer. Okay? So, what we are going to say is we can disregard the velocity boundary layer, right, when calculating the thermal boundary layer, right. So, we can disregard the velocity boundary layer when calculating the thermal boundary layer, right. Then in that case, if we do that, okay, then what that means is that the velocity can be written as, right, the u velocity is nothing but free stream, okay, and the v velocity okay. Now, this is an expression, the expression for v actually, we get this from the continuity equation. We get this from the continuity equation. Okay. Then we can, from the energy equation, okay, then from the energy equation what we can write is minus y right. So, the energy equation kind of looks like this, you know, this, it looks like this, where, so basically, like I said, we have introduced, so what we said is that since, you know, the boundary layer thicknesses, thickness of the velocity boundary layer is very small, so we disregard it. So, what therefore what we will write is, so basically what we are essentially saying is that this, you know, this gradient in the velocity in this little delta x, we just disregard that. So, we basically say that it's just a free stream the whole way through. So, therefore, we say that this u thing, the small u is in this part, right, which we said. So, that u is nothing but the free stream, right, and the v is nothing but this we get from continuity. Okay. So, that, and so therefore, we use this into the energy equation, and this is what we get, right. So, now what we will do is we will introduce a similarity variable, okay, as we talked about earlier. So, introducing, right, similarity variable. Okay. So, when I do that, okay, so eta is y, okay, okay. So, I am just writing a lot of things, okay. So, you must be wondering, now what is this now? Okay. So, let us see what this actually is. So, there are quite a few terms here, you are probably wondering what this is all about. So, I have taken the thermal diffusivity term here A, okay, and I am doing this integral going from x naught to x of the velocity u infinity, right. So, u infinity seems to change as we go from x naught to x dx, and this is something that I am integrating and I am multiplying it by the thermal conductivity. Okay. Now, just for a second, let us just go back and look at the formula of the thermal conductivity. So, the thermal conductivity was something like this, right. Thermal conductivity is something like that. Okay, fine. So, now let us see what this actually even means. Let us define this a little bit. Okay. Now, what does this x naught, x and so on and so forth mean? Now, what we will do is, now, so let me draw this, flat. So, say I got a plate like this. I really don't know how to draw straight lines anymore. So, this is the flat plate. Okay. Now, and you basically have a free stream coming in. Okay. You got a free stream coming in, so on and so forth. Okay. So, what happens is that you have a free stream coming in, okay, and there is something else here. Okay. Now, okay. Okay, now this axis, okay, now I'm going to draw this. This axis is basically of the wall temperature, okay, and this of course is x, right. Then, now here, this bit, right, it is nothing but T infinity, right, and around this point, okay, around this point there is a jump, and the this is the wall temperature. Okay, this is the wall temperature. This is the wall temperature. Now here, so basically this location is x naught. This is x naught. Okay, so and this could be x for that matter. It could be anywhere between x. So therefore, what you're saying is that this. So now this is something. This temperature profile thing is something that you haven't seen earlier. This is something we're using right now, isn't it? So you've been seeing this earlier. So you have a flat plate and you have a velocity profile, right, comes in, and then it forms a boundary layer. So let's do that. Okay, so let's do that. We're going to just say that there it forms a boundary layer. Okay, so it just forms a boundary layer, and if at any point, at location, so I were to draw the velocity profile, it would look something like that. so on and so forth. So this is v infinity x, so this is v infinity. Right? So this is my velocity profile. Now, so this and from this 0, okay, this point is 0, so on the origin of the flat plate till about x naught is what we get. Now from x naught you have a jump in the wall temperature, isn't it? So you have a T infinity and a TW. So T W minus T infinity is something which is positive. Therefore you have a theta, right? So theta from x naught. And so therefore what happens is that because that is so, it was at wall temp, it was at free stream temperature, but now it's not, right? It is at a different temperature, which is at the wall temperature. So therefore it will try to get to T infinity, and hence therefore there will be a transfer of heat across the boundary layer, right? And therefore we will have a thermal boundary layer. So that's basically the point, isn't it? So then what you're basically saying is that we will have something like this as well. These are not parallel or anything. Okay, so then basically what I'm saying, right, that okay, so this is basically free stream, and this bit, this is the wall temperature. Okay, so then basically what I am saying is that this is the edge of the velocity boundary layer, and this is edge of the thermal boundary layer, edge of the thermal boundary layer. Okay. So basically I can sort of label this. Okay. So when I say x here, so when I say x naught here, well, that x naught is basically this. Okay. Now that x naught could be 0 for all you want. So it would have, that there would be no discontinuous temperature jump. So it would basically start from there. Okay. And yes, right. So however here so what you can basically see is that every time there is a TW minus T infinity, that's when we start having a thermal boundary layer, and which is in this particular case starting from x naught. Okay, so I could sort of this picture is, so I could sort of label this and say this is development, okay, of the velocity and thermal boundary layers, okay, for a discontinuous jump right in the wall temperature. In the wall temperature, right, at position this, right. That's basically this picture what it is telling you, right. So therefore if you see here, so what we are basically saying is that from x naught to x, so basically depending on how far you want to go on the plate, so starting from x naught, that's the start of the discontinuous temperature, you integrate the integrate the free stream velocity, okay, and then you multiply that by the thermal diffusivity, okay. So and this shall give us, this shall basically give, that's how we define the similarity variable, right. So then what's the following ODEs are obtained for theta 1, okay. Now the following ODEs are obtained for theta 1, which is which varies as x and y, and also where, of course, where it starts, isn't it? Of course, I mean, it varies because of that as well. And so does eta, okay? Right, which is equal to eta, and that is equal to t minus t infinity dw minus t infinity, right? If I do that, what I get is the following: theta double dash plus 2 eta theta dash is equal to 0, okay? The boundary conditions being theta at 0 is equal to 1, theta eta tends to infinity is equal to 0, okay? Now, so that's basically my equation, okay? Now, solution, so this is now coming down to math and calculus. Now, solution to the above is the following in a function. Now, solution to the above is the error function, okay? So, what is that? So, error function eta is 2 by under root pi e to the power, okay, and this is possible for this case, okay. So, therefore, when we solve this, right, so we do all the math, etc., and we solve, when basically we use the math and we solve this, then we get an expression for the Nusselt number. What is that? And that is by lambda, which is equal to u infinity x into L by under root pi nu x naught x u infinity x dx under root Prandtl number. Okay, now this is very interesting. So we get an expression for the Nusselt number. Okay, I'm going to call that as 3. Now, so what does that mean? So if I do get that, then what does that even mean? Okay, so what that basically means, for example, that from 3, right, from 3, for a flat plate, okay, at 0 incidence, okay, alpha, whose function of x and x naught is equal to free stream lambda square pi nu x minus x naught under root Prandtl number, right? Right, and this alpha is basically coefficient of heat transfer. Okay, so basically what we're saying here is that if we, when we look at these, so when we look at these cases here, you basically come down to, you basically are able to write out simple equations, very simple. You are able to get these simple, straightforward, formulae, with which then you can, get more information about the thermal boundary layer, right? So, so in this particular case, so that's all you need to do. So this is your coefficient of heat transfer. Okay, so it should be a simple process to solve this. Now this thing, this equation that we wrote down for for the flat plate here, for Tw is equal to a constant. Now one could also write this in terms of if the wall temperature is a function. I mean, it could be like it could be a function, an exponential function, or it could be basically given. Okay, one could also use that kind of a definition and do that. Okay, so that's pretty much what I wanted to talk about in terms of for the first case, right, where we talked about the Prandtl number being very small. So if the Prandtl number is, in this case, is very small, this is the case. So yeah, like I said, if that happens, so we should be able to still boil it down to simple formulae with which we can get more information about the thermal boundary layer. Okay, so I will stop here, and of course we'll take up the next one, which is Prandtl number very large, like we said, in the next module or so. So thanks.